So we're going to have 4 courses this week, and every course is going to have 1 lecture during the day. So this is lecture 1 of the first course, which is on class field theory. And the afternoon will be exercises, and the whole idea is that actually we don't expect you to sort of really absorb everything of these 4 courses in 5 days if you haven't seen much about it. It's important that you get a feeling what these things are about, that you've heard about it, and that you sort of know which people to ask, where to look, and maybe already sort of get your personal experience actually dealing with these things. It's going to be all very concrete. I mean, if you do Galois theory, it's one theorem, you can write it down, learn it by heart and say, now I know Galois theory. It doesn't work that way in mathematics. It's a theorem that you need to use. In the same way, there's going to be 4 lectures on class field theory, and you can just project the main theorem of class field theory and say, that's it, and now you know what it is. Personally, and I'm not the only one, I think the sort of a hands-on feeling is important, so there will be lots of exercises that do with actual computations. Of course, I'm so old, almost as old as Henri, that we know that even without Paris, you can still do things just by hand. So many exercises can just be dealt with by hand. They're not at all computational. Some of them actually are, and then you may want to use Paris or Magma or your favorite brand of computer algebra system to actually sort of get numerical data. And that's, of course, is towards the arithmetic statistics, since we're now going to do theory this first hour, but next week you'll see that once you're can very easily find, say, class groups or class fields, you may start wondering what these animals look like sort of on average and how they should behave roughly, and you come up with statistics. And the main thing about statistics, that's going to be the topic next week, is that things behave randomly within the borders of the theorems that exist. So as a mathematician, you have to first sort of find the theorems that exist, and if you cannot prove anything more, then you hope that all the rest is random. And also, finding out what random means is not at all trivial. Think of Cohen-Lenstra. What is a random group? That's also a kind of mathematics. It's more like philosophy. And you come up with a model. Yeah, that happens in natural sciences. And you're going to test it numerically. And if it doesn't work, there's maybe a theorem that is sort of preventing it from being true. And you try and prove things. In the end, you want to prove things being a mathematician. Okay, that's where we're going. For now, we're just going to do a sort of an easy introduction. It's 9 a.m. on a Monday morning to class field theory, which has a reputation of being somewhat complicated because it's typically not included if you do algebraic number theory, sort of your first course. You will learn about number fields. In your second course, you will do local fields and ideals, and then beyond that, there's class field theory. So people think, oh, this must be something really complicated. But actually, it's almost a century old by now, and the theorems are not only rather accessible, you can also use them in practice. So my idea is, of this first lecture, to give you an introduction to how you get to class field theory. What it says, it will be fairly classical, meaning that I will use the old-fashioned language that it was created in a century ago. Tomorrow we'll make it slightly more modern, go for ideals, which is the same language but phrased differently. So you shouldn't view it as a big difference, it makes it slightly more modern. On Wednesday there will be René Schoof, who will tell you about the cohomological formulation. Again, that's reformulating the same theorems in a different way. And then we will apply them in the last 2 lectures to do the classical reciprocity laws and do something modern on Friday is the idea, which is called radii reciprocity, which has been proved rather recently, finally proved I should say, and also has been used recently in improving Cohen-Lenstra conjectures for 2 class groups of quadratic fields. So that is the plan, and let me now start with the easy introduction. So algebraic number theory is a prerequisite, and if you remember, people tell you, why would you need algebraic number theory? That's because in number theory, we typically solve equations, say in integers or in rational numbers. So if you pick your favorite equation, and I think many number theorists that have to mention their favorite or the world's favorite equation, that's going to be this one. And that's an equation that you're supposed to solve over the integers. So that's the Fermat equation. You're interested in solutions over Z. And Fermat had a conjecture, theorem, which took a long phrase in Latin in those days. Actually, writing this down is already something relatively modern. Euler could do this, but not Fermat. He wrote Latin and just had phrases about nth powers. Writing it like this is extremely efficient, and that's something that we owe to people like Euler. This is a century later in the 17th century. In the 18th century, people also discovered that there were complex numbers, and in the 19th century, so I'm mixing it up, I think 17th Fermat, 18th Euler, so 19th century we're now. That's Kummer is sort of the beginning of what you should call standard algebraic number theory. And the observation is that you may want to do this over the integers, but if you allow yourself complex numbers, then you can actually factor it z to the n minus x to the n as a product of linear factors. And what you need to do that, there's the z here, I guess, and the x there. It's a product of n linear factors. Maybe I want to call this m. Let me try and stick to m for this one. Sorry. And this is over the complex number. What you need is a primitive nth root of unity. So if you know what the exponential function is over the complex numbers, you can define this complex number, e to the 2 pi I over m. That's a primitive nth root of unity. And then your polynomial expression, these are all algebraic equations, we're solving Diophantine equations, becomes something that is a product of linear factors, but you do need something outside the rational numbers. And if you go for complex numbers, you're just doing geometry. So in modern terminology, whether you solve equations or go for rational points over whatever base field on your curve, that's just phrasing the same statement in more or less fashionable ways. And Kummer discovered that if you want to do this, you don't need, I was about to say this is over the complex numbers, but these elements actually are not just random complex numbers, they live in a number ring. And in this case, it's going to be a cyclotomic ring. So this is our first example of a number ring. And then what you need is a theory that does for this number ring what ordinary arithmetic for z that you have known since Euclid, more or less. So here you have primes, you can look at factorization, all these sort of well-known things. The question is, do you also have them for these rings, in this case cyclotomic rings that Kummer came up with? So the algebraic number theory, A and T, is essentially doing arithmetic like in Z, but now you have to develop them for number rings. And number rings are things that look like this cyclotomic ring. And it's a whole theory, so that is your first course in algebraic number theory. And these number rings live inside things that are called number fields. So there's the field Q zeta m, the mth cyclotomic field. And in general, what does algebraic number theory tell you? Rather than working in the rationals and then divisibility is phrased in terms of integers, so you need a ring rather than a field to talk about divisibility, you're going to extend it to finite extensions of the rationals called number fields. So, and they always look like Q alpha. So you can always get them by adjoining something like zeta m. So typically I will have a polynomial f, which is a reducible polynomial of alpha over the rationals. And just by replacing it by a multiple, I always take it to be monic, with integral coefficients, monic irreducible. So that's the way you get a number field, and that's not because you like number fields, that's just because the equation at hand forces you to work in a ring which is bigger than Z, but not that much bigger. So these rings, in here you will have a ring Z alpha. This is an extension of degree n, where n is the degree of this irreducible polynomial, and Z alpha will be a module which is free of rank n over Z. And you try and do arithmetic in Z alpha as you do it in Z. And what does the theory say? So this is what was proved by Kummer and his successors. So the main points are, first of all, it does depend which alpha you take. This in a way is the right ring if you're working inside the cyclotomic field. The reason being that rather than Z alpha, you have to find a ring which is called the ring of integers. So find the ring OK, which is the ring of integers, in your number field. And that can be easy, as it is for the cyclotomic fields, or it can be much more complicated. For these rings of integers, yeah, this will be free of finite rank n over Z. So it looks pretty much like a cyclotomic ring, or like a ring Z alpha. And of course it also has a definition, it's the integral closure of Z in your number field. So this is the number field is called K, and the ring of integers is called OK. So you need to find that ring, and that's the ideal ring to do arithmetic in. Finding it, of course, may be complicated, but we'll get that in a moment. And what are the main statements of algebraic number theory for these rings? So, okay, there's first a problem, but also a solution, which is that if you want to do arithmetic, which is by divisibility and factoring, you need primes. So the word primes, in Z, they are just prime numbers, and they're typically taken to be positive. For this ring of integers, you go for prime ideals, and you still call them primes. And then the statement is that, okay, it may not be a unique factorization domain, but it has at least unique prime ideal factorization. Meaning that every non-zero ideal in that ring can be factored uniquely up to ordering as a product of prime ideals. So it pretty much looks like the ordinary factorization. The only thing is that you have to deal with ideals. And when you deal with ideals, there is, first of all, the question, is that really different from elements? Since if these ideals are principal, at least they have a generator, which is unique up to units, multiplication by units. And the answer is, it's almost correct. Namely, there is a finite abelian group, the class group, which you also need to define, the class group of K or of OK, whatever you want, which is gotten by taking all the ideals, so that's the non-zero OK ideals. You take them up to equivalence, that is up to scaling by elements. So you can phrase it in two ways, everything inside OK, or you make it a group first, you go for fractional ideals, and then you mod out by the so-called principal ideals. So fractional OK ideals modulo principal, just that do have a generator. And this is an abelian group, and the first important statement is that this is actually a finite group, which means that you don't have what you would have liked, just a unique factorization domain, but you're not that far away. It's called the Dedekind domain. I mean, all the big names sort of pass in algebraic number theory. Kummer, Dedekind, Kronecker, Weber. You're going to see them all on the blackboard, or at least you can hear them today. And secondly, as I said, if ideals are principal, they have a generator which is unique up to units. So also the question is, what is the unit group? And there is also a theorem which is called the Dirichlet unit theorem. And Dirichlet showed that this group is finitely generated, meaning that it has a finite torsion part, that's called mu k. These are the roots of unity. And that's actually finite, a finite cyclic group, times the number of free generators. And if you want to specify that number, typically people look at embeddings of your number field in the complex numbers. Just like this cyclotomic ring is a subring of the complex numbers, but actually there will be more embeddings, and you look at all of them. And some of them actually land up in the reals. That's called a real embedding or a real prime. And if it's in C but not in R, it's called complex. And then they come in pairs, complex conjugate pairs, obviously. And if you count them, there will be n embeddings with n the field degree. And if you call the number of complex embeddings S and the reals R, then you see that R plus, these are pairs, R plus 2S equals the degree n of K over Q. These R and S, that's the signature of the number field, so that's its Archimedean character if you want, determines the structure of the unit group, since the free rank of the unit group will be R plus S minus 1. These are all very old and classical theorems going back to the 19th century. And when people like Henri Cohen started creating programs like Paris or systems, actually finding these objects was something that people, especially older people, did by hand in those days. And some other people never did it at all. They were happy with the theory and said, okay, that's the theory, now I know what these things look like. But in general, it's not so easy. Namely, if someone throws a polynomial at you because there is some number field that comes up in whatever you're doing, then finding this ring of integers already is a step which is not completely trivial. Since what do if you're confronted with some monic irreducible polynomial and the associated number field k? Well, you just hope that Z alpha is anywhere close to the ring of integers. And you need to do some sort of linear algebra over Z. You define things like discriminants of such an order and of the polynomial, and you discover that the whole thing is something finite, if you look at the discriminant of your polynomial, so delta f is the discriminant of my polynomial f, and I assume that you know what a discriminant is of a polynomial. That's going to be an integer, since my polynomial is monic in Zx. And that discriminant tells you a lot about the number field. In particular, it sort of tells you the difference also in a way between Z alpha and the ring of integers. This falls apart as the index, since the ring of integers will contain Z alpha. Since the ring of integers is the maximal order, so it will contain any ring Z alpha if this alpha has a monic irreducible polynomial. This index is going to be finite, and actually it factors like this. And the second delta is again called the discriminant, but that's the intrinsic discriminant of the number field. So this is the discriminant of f, and this is the discriminant of k. It's one of the main invariants of a number field. Actually, it tells you which primes are going to be ramified. So the size of a number field is determined by its degree and its discriminant. And then typically what you need to do is actually figure out which primes occur in this index, which is okay in small examples, but if you happen to do something like the number field sieve, you may have an f which has a discriminant which is way bigger than the number you're trying to factor. So if delta f has 1,000 digits, step 1 factoring it is not a good idea. Which means that now in practice, people often use the ring Z alpha, if need be, rather than OK. Which means that you have to sort of review all these theorems and see what remains if you do it for Z alpha. And the general feeling is that there's only finitely many primes, yeah, so locally it's almost always correct, there's a few bad primes, and if you desingularize there, you get the full thing, but you may not need to desingularize if the point which is singular is sort of far away, you never encounter it, you simply don't care. So Z alpha, for practical purposes, you may enlarge a little bit, and then it will behave as the ring of integers. And then computing the class group is also something which is, from the theory, it's a Minkowski type argument that is going to be finite. It will just tell you that in the class group, every ideal class in the class group contains an ideal of an integral ideal of norm no more than the so-called Minkowski constant of the number field. And the Minkowski constant of a number field is some multiple of the square root of the discriminant. So that is something explicit times the square root of the discriminant. Which means that to find the class group, you just look at all the primes up to the Minkowski bound, you factor them, and you find all relations. So you generate relations, you find the class group, and at the same time you find the unit group. So computing the class group and the unit group is just one and the same algorithm. And it's somewhat complicated. So this is something that people have seen, I don't know what it looks like, something like 4 over pi to the s. It's just completely explicit, right? N factorial, n to the n square or something. So this is something that is, well, it's an algorithm you can now think of yourself. Doing it is not so, maybe not so easy. And at the end of the day, you get an answer, which is the class group. So in arithmetic statistics, this is one of the main things. You can ask similar questions for, say, elliptic curves or abelian varieties. What do you expect to get, say, for the Mordell-Weil rank? In this case, it's called Cohen-Lenstra. There will be more about that next week, I guess. So you have something that you can now compute, thanks partially to all these computer systems. So there's massive data. So class groups and number fields, there's now millions of them in the LMFDB, which is the L functions, modular forms database. Thank you, Samuele. You'll get in touch with it, I guess, during the exercises. There's massive data, and we can sort of wonder, what do class groups look like? But at least you should know in principle how to compute them, and you do it a few times by hand, and then you trust that people, that people who create these databases know what they're doing. But still, sort of knowing which questions you can ask to a system and which you can do yourself and what is feasible and what is not, that's important knowledge for any number theorist these days. Okay, so that is algebraic number theory. And let me get back to where we need to go, namely cyclotomic rings. Since in our particular example, there was a cyclotomic ring. And cyclotomic rings, cyclotomic so means gotten by the root of unity, are in many ways easy. As I said, this is the general purpose algorithm for Z alpha. What you need to do, first of all, you don't need to think what Z alpha and what the ring of integers is. Namely, if you take the mth cyclotomic field Q zeta m, then its ring of integers is in fact equal to Z zeta m. And the polynomial f that gives rise to it is the mth cyclotomic polynomial. So step one, already finding the ring is easy. And of course, then the general theory sort of applies. So typically these are totally complex fields. They don't have real embeddings if m is at least 3. And in principle, you can compute all these things. And the second thing that also gives you a big handle on everything around is that you have a group of automorphisms. There is a group acting which is Z mod m Z star. The invertible residue classes modulo m. And why is that? Well, here I chose a specific complex numbers in terms of the exponential function. If you're a little bit more algebraic, then you know that the polynomial f involved, which is the mth cyclotomic polynomial, actually factors as zeta m to the I, where I ranges over Z mod m Z star. So the roots of the irreducible polynomial are just powers of a given primitive mth root of unity. And algebraically, of course, these are indistinguishable. Yeah, they're just the same thing. Meaning that you have automorphisms, namely if you have a residue class A, it will correspond to an automorphism, phi A, and what it does is that it sends zeta m, it raises it to the 8th power, which is well defined for any A co-prime to n, m, and it only matters modulo m. And in fact, if you do Galois theory, that's another great 19th century invention, this actually becomes the Galois group of the mth cyclotomic field over the rationals. And having this group action by an abelian group is a major asset. It allows you to look at all the objects that you encounter, like the ring of integers, its unit group, the class group, the ideal group, the principal ideals. There's an action of the group all over the place. And that means that rather than talking about groups, yeah, group is the same thing as a Z module. You want to use fancy terminology. And what happens is that if you have a Galois action, and in particular by an abelian group, these things become, so this group has a name then, whatever, the residue class is modulo m, Rm, with the E's notation, you get modules over the group ring ZRm. And if the group is abelian, as it is in this case, you typically look at the characters and you can split all the objects that you encounter into eigenspaces if you're lucky, and the structure is much more, is much easier to hold in your hands than it is for arbitrary number fields. So in this case, the theory of cyclotomic fields is much more explicit and, yeah, how should I say, more accessible than for general number fields, even Galois fields. And that's also very visible if you go for the splitting of primes. Yeah, what you typically need to do, if you want to do arithmetic in such a big ring, here you know what the primes are. Well, more or less, right? There's a prime number theorem and you sort of feel that you know what ordinary primes are. But the prime ideals of such a ring, that's more complicated. Typically you start with the rational prime, so we're up there. And then the question is, yeah, so splitting of primes is a key thing that you need to know. Meaning that in your number field, if it's a general thing, Q alpha, as I said, you look at this ring Z alpha, you hope it's the ring of integers. And given P, you want to know which primes lie over P. And the main theorem there, again 19th century, is that if you stay away from the singular primes, the ones that divide the index all the way up there, yeah, so for primes that do not divide this index, and if you may not know what the ring of integers is, but at least for any prime you can check whether it divides the discriminant of your polynomial. And if it doesn't, then you certainly know it's not in the index. And if that's the case, then splitting a prime is essentially factoring the defining polynomial modulo p. So p will factor as a product of primes to certain exponents. And the question is, can you find the primes lying over P explicitly? The answer is yes. For the non-singular primes, this factorization comes immediately from the factorization of F bar, so that's F modulo P. If you factor that over the finite field, so that is, say, gi to the ei, I is 1. These are monic irreducibles, but now in Fpx. Then the theorem, which is called Kummer-Dedekind, I think so, tells you that the primes lying over P just come from the polynomials that divide F in Fpx. Namely, explicitly, the correspondence is as suggested, and Pi is just generated by P and gi alpha. So factoring is something that depends on, it's just factoring the defining polynomial mod P, essentially, apart from finitely many primes. That is completely general. And if you're dealing with a Galois number field, as we are for the cyclotomic fields, life is a little bit easier in the sense that the outcome is very regular. And by this I mean that once you have one prime lying over P, you sort of have them all, since they're all going to be isomorphic. Namely, if you have your prime P and you take the extension primes, if there is a group, the Galois group of K over Q, acting on everything, then this action of G is going to be transitive. Meaning that all the primes over P are conjugate, isomorphic, and they're all have the same behavior. So then typically there's this famous formula that you learn that you can always count the number of primes in this set. It can be anything up from 1 up to the field degree, and you have E, F, G, and these F's and G's have absolutely nothing to do with the F and G that you find there. They're canonical letters that are traditional. This is called the ramification index. That's the only letter which is the same as over there. So all the primes dividing P, if they occur with a higher exponent, they all have the same exponent E. F is called the residue field degree. Namely, every prime has a size, meaning that if you look at OK modulo the prime P, that's the residue class field, Kp, that will contain Fp, obviously, and it's a finite field extension, and the degree is by definition F. So this is again F, and it has nothing to do with the polynomial that I called F before. And then G is just the quotient. This is the number of primes that actually do divide P. This is generalities for arbitrary Galois number fields. And an all-important issue is that if you look at the action of G on the primes extending P, then you have the stabilizer inside G, the decomposition group. And that subgroup actually has an identity. This is actually the same thing as the Galois group of the residue class field extension, Kp over Fp. And this is an extension of finite field which is generated by Frobenius, raising to the power P, Frob P. X goes to x to the P. That's the way things work for finite fields, and as I said, in Galois extension you can just raise this prime P at least if the prime P is unramified. So this is, in general, it's a surjection, let me put it like this, and it's an isomorphism if P over P is unramified, meaning that the exponent is equal to 1. Okay, so that means that you always have Frobenius elements. And if we now get to the cyclotomic fields, it's even more explicit. So now we take the number field equal to Km, the M cyclotomic field, and you discover that in this case the Galois group G is Z mod M Z star. And that means that inside G there's always the stabilizer of the prime P, and in this case raising to the power P is just the residue class P mod M. So for primes not dividing M, you know exactly what that group is, and you also know, of course, that in fact just you see that if you have fp zeta m, this finite field extension over fp, the degree is just the order of p in z mod m z star. So for the exercise, let me just write down quickly, since we don't have a lot of time, but this is something that should be your bread and butter. Cyclotomic fields, they're sort of the prime example of the class fields we're going to work with. So if you take your favorite example of m, and I think my favorite example today is m equal 20, then how do you analyze a cyclotomic field Galois theoretically? So Q zeta 20. First of all, you decompose m into prime powers. It's going to be a compositum of Q zeta 4, which people know as Qi, and Q zeta 5. So the degree is going to be 8, 2 times 4, and this is a cyclic extension of degree 4. Z mod 5 Z star, right? So I'm actually, the group Z mod 20 Z star, by the Chinese remainder theorem, is a product of two groups corresponding to this being a compositum of two cyclotomic fields of conductor 4 and 5. And to make this completely explicit, you have this Galois theory. And here it's easy, since you know that there's a quadratic field ramifying only at 5, which is real, Q square root 5. And then you just take composites, Qi square root 5, Q square root minus 5. This is a standard V4, for instance. And then you think, is my diagram complete? And one of the exercises this afternoon is also, why isn't this diagram a Hasse diagram? Why isn't it complete? Because for cyclotomic fields, more generally, that's one of the exercises, such a diagram, there's the field diagram and there is the group diagram, right? Galois theory tells you that subgroups of Z mod 20 Z star correspond to subfields of Q zeta 20. So exercise, you find all these things, 11, 9, minus 3, something like this. And such a diagram, you can always put it upside down and it should be symmetric. So there is something lacking here. It has to look like this. And in fact, that's the group minus 1 with a real cyclotomic subfield. The reason that I'm writing this actually down explicitly is that it's essentially one of the exercises. You have to do something similar and stare at these various extensions. These are all subfields of cyclotomic fields. So there's group action that you should understand completely. And in particular, the next thing we're going to talk about is the splitting of primes. And that will be essential for arithmetic statistics. Namely, you can wonder, given your primes, what Frobenius will they have? And just to get an idea, for Z mod M Z star, which we now identified as the Galois group of this cyclotomic field over Q, we know that P mod M corresponds to the Frobenius automorphism of P. And I should have said that this Frobenius, in general, it depends on the prime over P. It's a stabilizer of a prime over P. And this is a transitive group action. If you change the prime P, if you take a different prime over P, you get a conjugate subgroup. So in general, such a decomposition group is only determined by the prime P at the bottom up to conjugation. But we're dealing with abelian extensions, which is actually the whole the key sort of to class field theory. Abelian extensions are so much easier, it only depends on the prime at the bottom. So this P is really an element, and it has a fancy name in general. It's called an Artin symbol, because Artin realized that this Frobenius, this association, is the essential thing. The Frobenius element is somewhere in the Galois group, and Dirichlet already, and that is the beginning of statistics if you want, showed that there is equidistribution. If you throw away the finitely many primes that do ramify, that are not co-prime to M, then you're left with a set that you can sort of divide it over the various buckets, and the equidistribution means that each class has the right density. So that means that every element corresponds to a set of primes P which is then congruent to A mod M, which has the expected density of density 1 over the order of the group, which is the Euler phi of M. And density, well, there's two definitions. The one that actually is in the proof of Dirichlet, that's called the Dirichlet density. Let me skip the definition for now. There's also a density you would define yourself, which is the natural density, which is a somewhat stronger concept. Either way, Dirichlet proved that every residue class gets its share of primes exactly as you think. And that is a key property. Once you can relate the property of your prime to splitting behavior, and splitting behavior means Frobenius element in a Galois group, then you immediately get equidistribution. In this case, it's very classical. It's the theorem of Dirichlet on primes in arithmetic progressions, but it's valid in a much wider context. So starting with Dirichlet, that is in the 1840s, I think, that the primes are equidistributed over the residue classes modulo M. You can look at the same question over Frobenius elements in Galois groups, and the final result is the Chebotaryov density theorem, which is a key theorem that we won't prove, but we will use all the time. So that's the theorem which says that if your number field is Galois, actually, let me just do it immediately for L over K for an extension of number fields rather than over the rationals. If the number field is Galois, so you have a Galois extension, K over L is now Galois, that is now the setting, I just replace Q by K. Then you can always wonder, for a given prime P of your ground field, what is the Frobenius element? And as I said, it's only unique up to conjugation in general. It's a generator of this stabilizer. And that means that you can only ask what it is up to conjugation. And that means if you take a subset of the Galois group stable under conjugation, and you look at the set of primes P of K with the property that it's Frobenius lands in C, that is well defined because of the condition, and well, it has density exactly what you think. How likely is it that a certain Frobenius is going to be equal to an element in C? It's just the fraction inside the Galois group. I just say density. As I said, there's two versions. There is the Dirichlet density, there is the natural density. It's true for both. The natural density is much harder to prove, but it's always true, and it gives you, if you want, a first handle on how primes behave sort of statistically in a number field extensions. Frobenius elements are random in the sense that they equidistribute over the Galois group. And that's a key theorem, so that has been in the making from the 1840s, and the proof by Chebotaryov is from 1924. And just like the Dirichlet theorem, the proof is analytic. We're not doing much proofs here, but what you need to do to prove this, the way Dirichlet did it, is that you define functions called L functions using the characters on the Galois group. As I said, if you have an abelian Galois group, you have characters on them, and you can do that to decompose your whatever you're looking at. And these L series, complex analytic functions, they provide a factorization of the zeta function of your cyclotomic field. But analytic means, yeah, so this is the thing that had been pioneered by Riemann, the zeta function, the L series. You discover that you get an equidistribution result, and the density that you find that comes from the proof is exactly the reason that you have this funny Dirichlet density. It's more like residues of complex analytic functions, and it's not the natural density. So this is a key result that is extremely important. And many of it has been used already. I mean, this is the final result, that is for arbitrary Galois fields. But Frobenius, for instance, already, yeah, there's various corollaries. Let me just mention one. Corollary. If you look at, if you have any Galois extension of number fields, and you look at the primes P that split completely, in this extension, then you see that's a special case where C is just a unit element of the Galois group, since splitting completely means that the Frobenius element is the unit element, trivially. This set has a density 1 over the field degree. So for instance, yeah, and these results have been extremely classical already. If you take a cyclotomic field, you get exactly, for instance, the equidistribution result of Dirichlet. Yeah, so primes 1 mod m, that split completely in the cyclotomic field, have a density 1 over phi m. Also, if all the primes 1 mod m split completely in your, yeah, so if, not a corollary, think about it, if all, or almost all primes 1 mod m split in the extension L over Q, then the reason is that L actually is contained in the mth cyclotomic field. And let me now finally then get ready for the key statement on cyclotomic fields. Since we know how to deal with cyclotomic fields, the splitting is easy. It just depends on residue classes modulo m. And now we use this water machine. Even though I'm from Holland, I'm used to this. This is so fancy. This is German style. You only find it, I think, at Serum, the only place in France. Whoop. Yeah, I was a bit too technical. So the statement that we now need, that is the theorem, which is also 19th century, even though the proof is by Hilbert. So the theorem was discovered by Kronecker. And there was that's the middle of the 19th century. Weber gave a proof in the 80s, which was still not complete. And Hilbert, I think, used this theory of decomposition groups. And it says that over the rationals, cyclotomic fields have abelian Galois groups, but the converse is also true. Every abelian extension is cyclotomic. And by cyclotomic, I mean that L can be viewed as a subfield of Q zeta m for some m. So it's exactly the same thing. We can, if you know cyclotomic extensions, yeah, then you know in fact all abelian extensions. So abelian number fields having an abelian Galois group are extremely accessible because they are subfields of cyclotomic fields. And I don't have time to say anything on the proof. There's many proofs. The one by Hilbert is sort of classical Galois theory of number fields. You can also do it locally. Yeah, tomorrow we're going to talk about local fields, not today. And the key step is always, in the end, you modify your L with roots of unity, all kinds of twisting, and in the end you create a field over the rationals which is going to be unramified at all primes. And then there is this famous Minkowski type result. If, yeah, so the proof, the key step, if is totally unramified, meaning that no prime ramifies, then in fact Q is equal to L. There's always ramification over the rationals. And that is the key step in understanding why all the extensions are in fact cyclotomic. That's not much of a proof, but it's something that you should realize, and this is exactly which is no longer true over arbitrary number fields, which is the direction we're heading right now. Since what is the main theorem of class field theory? Let me just put it here. Class field theory. It is a theorem that replaces Q by an arbitrary number field. So, and it says that so you fix, just K is a number field. Rather than Q. And the statement is that every extension which is abelian, they're always finite, we're dealing with number fields, so abelian means finite abelian. And rather than being contained in the cyclotomic field, it will be contained in a field that is typically called the ray class field, modulo M. Let me just call it that for now. Every abelian extension is not cyclotomic, it is a class field. And what does it mean to be a class field? It is contained in a ray class field. So that is the word that's going to replace cyclotomic field, modulo a modulus M. Of course, there are certain words that need to be defined now. What is a ray class field and what is a modulus? But the key statement, so here we're saying that there is a group, an easily understood group, Z mod M, Z star, which is the Galois group of Q zeta M over Q. And you can understand your field L, which is inside. It's a quotient of Z mod M, Z star. And the key statement is that A mod M, well, let me call it P mod M maybe, will correspond to the Frobenius element of P. So you understand the Galois group and the corresponding splitting of all the primes. Yeah, since understanding the splitting of primes is knowing what Frobenius elements are. That is not something which is random, it is governed by congruences. Only knowing what it is mod M tells you what the splitting behavior is, and the reason is that actually L is contained in the corresponding cyclotomic field. And the same statement holds here. There is this easily understood group that I will define in a moment, namely the ray class group modulo M. It will surject to the Galois group of L over K, and the residue class of a prime P, at least if P does not divide M. Just like P mod M, I'm assuming here as well that P does not divide M. Ramifying primes are a bit more complicated, and we'll deal with them tomorrow if we do ideals. Right now, the class of an unramified prime in the class group determines its Frobenius. And this map is called the Artin map. So associating a prime to its Frobenius outside a finite set, those dividing the modulus M. This Artin map tells you exactly how to understand the arithmetic, the splitting behavior of the primes in an abelian extension. So abelian extensions are class fields, and that means that the splitting behavior only depends on the class of the prime, modulo whatever. Now there are a few technicalities, and that's exactly why some people think that class field theory looks complicated. But if you see it more often and you have 5 days to look at it, and hopefully by the end of the day you should think, oh, these ray class groups, they pretty much look like Z mod M, Z star. Let me give you a definition and see that indeed they do look a little bit like Z mod M, Z star. So what is the ray class field modulo M, and what is M? Since this P, the problem is that in the original version for the rational number field, you could just look at the generator of the prime. And you take the positive generator. Yeah, if you replace p by minus p, which generates the same ideal, you get a different Frobenius element. So there's a little technicality. You have to deal with units. And also, as you see, in principle, this might not be a principal ideal if you're here. So what the heck does this mean, the residue class of p modulo m? And the group you need to define, this Ray class group, you take all the ideals co-prime to m, and you mod out by principal ideals that are, let me maybe do Ray modulo n. What are these things? First of all, your m, as I said, is not exactly an integer. This is an integer, and that means it corresponds to a non-zero ideal of z, at least up to sign. This m will just be an ideal of the ring of integers, m naught. So this is a non-zero OK ideal. And you have something which is called the infinite part. And if you're dealing with infinite primes, you've encountered them if you did algebraic number theory. This is not actually an ideal. This is just a collection of real primes. And real primes are just embeddings of k in the real numbers. There's only finitely many, there were r of them up there, and you can include them sort of as extra data with your ideal. So it's an ideal with sign conditions. And that's called the modulus. By this I just mean I take all the invertible ideals co-prime to m, meaning that no primes in this m naught actually occur. Invertible OK ideals co-prime to m. That makes sense since I only want to define this for primes that are not dividing m. So finitely many primes have to be thrown out to get a sensible Artin map. And the key statement is that you can of course define this Artin map on the group Im, just because it's a free group generated by primes co-prime to m, just sending them to their Frobenius here. That's an easy map. So this Im has this quotient. Going from here to here is just trivial. The key statement is that it does factor via this class group, that the field is in fact a class field. And that means that the kernel contains Rm. And what is Rm? This is the group of principal ideals, principal OK ideals. So they look like alpha times OK, where alpha is any non-zero element. And this alpha is congruent to 1 modulo this modulus. And this modulo, well, some people give it a star to indicate that it's a little bit non-standard, this modulus. What does it mean? Oh, it doesn't work. It means that, just the definition, it depends on the primes dividing m. And if you have a prime that divides the infinite part, that's just an embedding sigma of k and r, it means that your alpha is going to be positive under that embedding. So as I said, it's just sign conditions. Alpha may be required to be positive at certain infinite embeddings, real embeddings, and these are the primes in the infinite part. And for primes that divide the finite part, m0, it simply means what you think. If you look at the valuation of alpha minus 1, it is at least the valuation, the number of primes, number of times your prime occurs in the factorization of m0. So it's a condition at finitely many primes, those dividing the modulus. And at finite primes is what you think. It's just multiplicatively saying that it's close to 1, namely this close. Vp is the valuation at p. Just count factors p, and it comes with sign conditions. So that may look a little bit, let me see. No, wrong. This is all extremely complicated, yes. So what do ray class groups look like? It's easy to check that if you go back to k equal to the rationals, then a modulus is just an integer up to sign, an ideal mz, maybe with this sign condition at the real embedding. So you see that if you take your m equal to mz, then the class group that you get is not z mod mz star, but you get it modulo plus or minus 1. The reason being that the units enter here because the generator is only unique up to sign. And if you take, so this is an exercise, I'm not going to spend time on it now. If you take m and the infinite prime, so whatever, infinity, and infinity is the embedding of the rationals in the reals, then this ray class group is z mod mz star. And in general, you see that what I did, this subgroup in IM, where of course you can just take all the principal ideals co-prime to m without imposing the 1 mod m condition, and in there is this so-called ray modulo m. This is what people call the ray. There's some discussion why it's called ray, let's not go into it right now. And you see that this ray class group has a quotient which is this quotient. And if you just take ideals co-prime to m modulo principal ideals co-prime, that's the ordinary class group. So all these ray class groups, they surject to the ordinary class group. They're just bigger versions. And how much bigger are they? Well, you have to see if you take a principal ideal, what it is modulo m, well, that's just what you do. You take your ring of integers O modulo m, and you take the generator modulo unit, because it has to be an ideal. And of course, this O mod m star, you know what it means if m is just an ideal. It's the residue class ring, you take its units. This formal collection of real embeddings means that O mod mo star is just the thing itself, m0 star. But for the infinite primes dividing your modulus, you take a sign map. So you take a sign p dividing m infinity. So for real primes, you also look at the quotient modulo the finite part, and here we take the sign under the embedding. So it's a bit of a funny group. Yes? Certainly, but I'm not proving anything. I just claim things are true. It is certainly true that you can generate any class group with the primes outside whatever. Sure. Yeah. Thank you. All right. So here are the new Z mod mz stars and the corresponding fields. So every m, if you look at the theorem, I'm about to wrap up. Every abelian extension is just a subfield of a ray class field. So every m does give rise to some field, hm is the ray class field modulo m. For which the Gelbach group is exactly the ray class group. So the equivalent, so if you write down your favorite modulus, look at this, this group, it actually does arise as a Gelbach group, namely of the ray class field modulo m. So the question now becomes, how do we find these ray class group? These are the analogs of the cyclotomic fields, and the main problem is that they do not come with explicit generators as they did in the case of the rational number fields. The course, which is starting in 15 minutes by Jan Vonk and Eugenio Rosu, will do complex multiplication, and they will solve this problem if k is imaginary quadratic. And in general, it's an open Hilbert problem. And in many ways, this is not a problem, since why would you need generators? Typically, you only need the arithmetic of the number field, and these groups that you just define on the side of k give you all the control that you need. I mean, you may still want to know, but in many cases, you don't care about generators. You can still deal with it. And once you know a Galois group, you can use it with the Chebotarev theorem to say how things distribute over the Galois group. So you're always in business as long as you're dealing with abelian extensions. So that is the key statement about class field theory. Abelian extensions of a number field are class fields, meaning that they're splitting behavior, the way the arithmetic is sort of set up, it only depends on P modulo M. And let me conclude in 3 or 4 minutes to prepare you for the exercises this afternoon. Class field theory is something that you can actually use to solve problems. And the problem that is the topic of a book by David Cox is that you look at the primes P stands for prime, that are of the form x squared plus ny squared. That seems like a very specific problem, and this is a set of prime numbers called Sn. And the question is, can you characterize these primes? And as you see, if you take your favorite easiest value, so n is going to be a positive integer. And this is a question that has been answered by Fermat. Primes that are of the form x squared plus y squared are just the primes that are congruent to 1 modulo 4. Which means that you know these primes, and you also know how many there are, if you believe Dirichlet at least. Primes 1 mod 4, that's just half of the primes. So the density, delta n, is 1/2. Easy theorem. Not in Fermat's days, maybe, he had to use descent, but nowadays, modern theorems, it's easy. S2 is an exercise this afternoon, and also 3 and 4, that's easy. S5 is the exercise that you find in my diagram. Since the reason that it has something to do with class field theory is that what you're asking here is that you're looking at a ring, z square root minus n, and rather than looking at your prime in P, you're asking something about its splitting behavior in this quadratic order. Then what you want is that your P decomposes as x plus y square root minus n, x minus. So this is just saying that P decomposes as pi times pi bar for a prime element pi in this quadratic order. And for small values of m, like 2, you may be lucky. This is a ring inside the number field q square root minus n. And if it happens to be the ring of integers, you're in business, you only need a classical algebraic number theory text, and you can actually determine how primes split. So for -1, it's indeed just being 1 mod 4 will make it split completely. But you may know that for z square root minus 5, there is this, if you take this for your ground field, the class group interferes. This is the popular example of a field or of a ring which is not a unique factorization domain. I'm almost done, don't get upset. That's 5 minutes of the coffee break. But these 5 minutes will save them half an hour for the exercises, so we're actually gaining a lot of time by it. So that means that if you want to have primes of the form x squared plus 5y squared, then you want that your prime splits in z square root minus 5, which is the ring of integers. However, this is not a class number 1 field, which means that you have a second condition. Not only does it need to split in this quadratic field, q squared minus 5, you also want primes to be actually principal. And that's also a class, but it's a class in the class group, not a mod 5 kind of thing, but a class like this. So you see that in this case, if you take k equal to q squared minus 5 and m just equal to 1, no primes dividing it, then already there's an interesting statement. So for m is 1, you see that the class group of a number field corresponds to the Galois group of some abelian extension, whatever, h over k, which is the Hilbert class field. And I didn't get to all the formal properties of this Artin map and which primes ramify, but as you can imagine, tomorrow we're going to see that the primes that ramify in L over K will of course be the divisors of M. And if M has no divisors, this has to be totally unramified abelian. And such a field exists for q squared minus 5. And it's actually staring you in the face. Here it is. This quadratic extension is the h that you need. And in this case, you can actually prove it. It is still not completely trivial. It's one of the exercises that is, of course, that two groups of order 2 are isomorphic is not so shocking. The fact is that the shocking thing is that the map is given by the Artin map. So the class of a prime in the class group of q squared minus 5 will determine whether it splits or not in this specific quadratic extension. Well, there's the miracle of class field theory. And you also see immediately that if you want to do this for arbitrary n, already for 4 is a square, right? If this n is not square free, you get an order in the maximal order, and you should wonder what the class group of that order is in relation to the groups that you have in class field theory. Well, since my time is up, I cannot tell you right now, but you'll find out this afternoon, or you ask the assistants, and then tomorrow we'll have someone telling us, because Ricardo Pengo is here on the second row. He is really important. His duty, I think, is to convince volunteers to present problems during the, what is it called? Exercise discussion session or something. So of course you're completely free, but this is really a Southern French style course. So your orders are being taken from Ricardo. We hired Italians to make sure you behave. Okay, now is a break. There's no break, sorry, we're going to have Jan. Okay, thank you for your attention.